By the way, for anybody in chat, I'll have chat right in front of me. If you have questions throughout this, I'll be able to see it. I'm looking right there. When I'm over here, I'm looking at slides, but when I'm here, I'm looking at you, chat. So welcome to Does This Look Weird to You? An anomaly, it's an introduction to anomaly detection. My name is Kevin Feasel. I am a Microsoft Data Platform MVP out of Durham, North Carolina. I also run a predictive analytics team here, and I have a blog called Curated SQL. The idea of Curated SQL is I try to find and link to 5 to 10 interesting posts per day on topics all across the data platform space. Check that out, curatedsql.com. I've got a few goals in today's talk. The first one is I want to help you understand the concept of anomalies. It's something that has a broad understanding at a really vague level, and I'm going to help you understand it at a slightly deeper level. We'll look at some techniques for detecting anomalies. We'll look at an anomaly detector built in the .NET framework, and then I'll use Azure Cognitive Services to perform anomaly detection. So, got a lot of content, plow right through it here. If you have questions at any point in time, put them in chat and I'll respond to them as soon as I see them. So let's start by asking, what is an anomaly? And at its core, an anomaly is an outlier. So technically speaking, it's a little bit more than just an outlier. See, an outlier is you're different from the norm. An anomaly is you're different from the norm in a way which is interesting to me. Now, that was a high-level conceptual definition. We're going to talk a little bit more about general concepts, but I will talk about specific technical definitions of anomalies as we go along here. Essentially, anomaly is I'll know it when I see it. I mean, you already see the anomalous entry in this image here. I don't have to show you. I don't have to point to it or explain it. You know what it is. This can get a little muddy at the edges, but it turns out that humans are really good anomaly detection engines. We have excellent pattern matching skills. We get confused from time to time, but on the whole, we do a really good job of telling when something is not the same as everything else. And one of the best explanations for this comes from the Gestalt School of Psychology, which was a set of German psychologists who did a lot of experimentation on how people see, envision, and work with different, especially visual elements, but they also did work with auditory elements and other senses. Essentially, how does sense information come to a person and have a person understand it and make sense of it? And one of their key insights is that our minds will apply known and expected patterns to what our eyes see. So we don't have to think about that as a square. Instead, we see the square and later on realize, oh yeah, that's a square. This leads to some Gestalt principles that we're able to take advantage of in everyday life. The first one is called the law of closure. The idea here is that's a square. Well, technically it's not a square. Those edges aren't closed in. However, you can look at that and say, no, that's a square. It's just not complete, but you complete it in your mind. The law of common region indicates that if I put some boundary around elements, you will naturally assume that they belong together. The elements in the gray box are different from the elements that are not in the gray box because otherwise they'd be in the gray box. It sounds a little silly, but it actually makes a lot of sense, at least to our minds. Figure ground. This is something actually, chat, I want to hear from you. When you look at one of these, what do you see? This is an image called Rubin's vase. So Rubin was one of the psychologists who did a lot of experimentation on visual elements. And an idea that he had was foreground versus background, or figure versus ground. And in different images, an element can actually take either position. It could be the background or it could be the foreground, just based off of what you see. So in the question here is, do you see a vase or do you see faces? And if I invert the colors, does that make a difference? So I've had some people say face versus vase for both of those, where, oh, I see the faces on the left and the vase on the right, or vase on the left, faces on the right. And regardless of which one you do see, yeah, it's obvious that both of them are in the picture. It's just a matter of which element we bring as the figure. The law of proximity says if things are nearer to one another, then they're going to be considered part of the same grouping. So if things are apart physically, if the proximity is distant, then they're going to be considered different, abnormal. I have a block of 3 blue dots. Those 3 blue dots, we consider them together, separate from that blue dot in the middle, which is itself separate from the 2 blue dots, which is itself separate from another blue dot. Why is that? It's because there's a little bit of distance between them. So our brains naturally associate them as 4 separate groupings rather than 2 groups or 1 group. We also group things based off of certain characteristics: size, color, and shape. And specifically, my recollection is that it is in the order of color, shape, size. So things that are different colors catch our eye immediately. You want to see that tiger that's in the jungle or that lion that's in the grass. You want to see that predatory animal, which is going to be a little bit different from the background. The colors will be a little different. So we see these and we naturally assume the yellow dots are together somehow. They belong together in some fashion. With continuity, this one's kind of interesting. We naturally want to follow the smoothest path when viewing lines. So our brains, if I made this in black and white, almost 100% of you would see a straight line right here and a little curved line coming down here. But the fact that I changed the colors on you makes it a little disconcerting, discordant. And that's our brain saying, no, that's not right. It's supposed to be different. And us having to rationalize, no, this really is orange and blue. They're separate colors. It's the different lines that diverge in a weird way. But we have to think about it. We do also perceive ambiguous shapes as simply as possible. If I show you just the picture on the left, you will see the triangle, the circle, and the square in them without me having to show you different colors. So, okay, we talked about Gestalt psychology, but how does that apply to detecting anomalies? And going back to humans being pattern matchers, we try to apply fairly simple heuristics to our visual inputs, which means I can show you this graph on the right-hand side. It was 1 week of NFL scores versus passing yards from 2019, I believe it was. Maybe it was 2020. Doesn't really matter. But you and I can look at that chart and say, yeah, there's definitely some correlation between number of passing yards and number of points scored. So it lets us make this cogent observation. It also tells us that if I happen to have Zoom It running, we're going to find out if I have Zoom It running. I do have Zoom It running. How about that? So I should be able to perhaps draw a line, but maybe I can't. Let's zoom in like this, then I can draw the line. So we've got a line. If I told you that that was the line, you'd probably look at that and say, yeah, that makes a lot of sense. And then you would see these 2 elements that are anomalous. They are at least outliers, and they're probably of interest to us. So I'm okay with calling them anomalies. So as a human, we just picked out the anomalies in this data set without any lines actually existing, without any strict concept of a model. We have just the bare bones idea and can already use our visual senses to determine that there's something of interest here. So we fit that line. Now that is actually the best fit line. And you can see that it's a little bit lower than what the human might say is the reasonable line, because those anomalies have pulled it down. So that's the general concept of what is an anomaly. Now let's start talking about some technical definitions into it. Because human concepts can be ambiguous. And if we want to develop something that is a little more concrete, we have to start with a more concrete foundation in terms of concept that we're trying to explain so that we can understand and implement it correctly. I'll know it when I see it. Works really well in some circumstances. It works really poorly when programming machines. Machines don't know what they're seeing until we tell them what they're seeing. So some things that do look strange to us, though, may not actually be anomalous. It may simply be that's just the way things are. And it turns out that it's perfectly natural for this event to occur. So as an example, if you're aware of standard deviations, 99.7% of events that follow a normal distribution happen within 3 standard deviations of the mean. But that also says if you have 1,000 events, you can expect that approximately 3 will fall outside of that. You will have outliers, and that is perfectly natural. It may be worth investigating to see if it's a legitimate outlier or if it's some sort of anomaly, some sort of maybe a corrupted data process or proof that your distribution is not actually normal. But it could, in the end, turn out to be just the way the luck of the draw happened. So, all right, let's dive into technicals. I already talked about distributions just a little bit. I've mentioned the normal distribution, but we have anomalies on a fitted distribution. We think this curve makes a whole lot of sense. And then there's this little bump out here. This looks weird. It is not in our expectations. It is well outside of our expectations. And it is interesting to us. So it's an anomaly. It does not fit within a certain distance from our midpoint of our fitted distribution. On a box chart or box plot, there is a separate definition of anomaly. So this is a box plot. If you're not familiar with this idea, we track several different measures on here. First one we get is the median. That's the 50th percentile of data in our group. So this is into year 2018. Median is 50th percentile. We also track the 25th and 75th percentiles. This forms the box. So the box is shaped by that. Then we have these whiskers. This is also known as a box and whisker chart. The whisker is 1.5 times the interquartile range. In other words, the length of this box, 75th minus 25th percentile, multiplied by 1.5, going in either direction, and that forms the maximum length of the whiskers. If there are no data points that are beyond, like right there, if there's nothing up here, the whisker will stop right here because that was the last data point. But in a case where here is our interquartile region, and we go 1.5 times that, and we have something that's further out than that, this is an outlier. So another definition of outlier, more than 1.5 times the interquartile range distant from the median. And 1.5 is a reasonable number, but it could be 2, it could be 3, it could be 1. And here's another example. A process control chart tells you whether or not something is in control. And what I mean by that, let's suppose you have some machinery that is drilling holes for screws, and it has to drill at a certain depth at a certain width because you have a specific type of screw that needs to go in there. And if you drill the hole too far out, screw is just going to fall in, so it won't work. If you don't drill the hole far enough in, it's going to be difficult to screw in. So we have a certain tolerance, a minimum and maximum width that's acceptable. And that's kind of represented in this gray box here. As long as you're inside the gray box, life is good. But what happens when you get outside the gray box? Maybe you start drilling holes a little too wide, or they're not going in far enough, or it's too deep or not deep enough. Well, at this point, you have a process that is out of control. So you're outside of the acceptable tolerant range. And that is another example of a technical definition of an anomaly. You are outside of the tolerances allowed for an operation, or the tolerances expected of an operation. So that's a lot of definitions. Now let's talk about what we might do if we want to work on a data set that might have anomalies in it. So first thing that I want to talk about is what makes for a good data set. Well, when you're looking for anomalies, there are certain attributes of your data which are really important. Ideally, you have one numeric measure. So one feature that you want to measure over time, over a category, whatever, but it's one thing. There are anomaly detection techniques that work on multiple features, that work on multivariate data. They are more complex, and so you'll end up putting more time and effort into them. They can also be a little bit more difficult to understand the math behind. But yes, you can do multivariate anomaly detection. No real question about that. However, if you have the choice between one variable and many variables, try to stick to one variable. Ideally, you have a fair number of data points. I'm saying at least 30. Why 30? Well, 30 is a rule of thumb. That is the number of samples needed to approximate a normal distribution when you're using the student T. So having a certain number of data points available gives you you're getting the beginnings of that law of large numbers, where if you have enough data, most things tend toward a normal distribution, or many things in nature tend toward a normal distribution. Or if you don't want to think in terms of normal distributions, having more data points means you have a better understanding of what is acceptable and what is actually an outlier. If I have 2 points that are very different from each other, but those are the only 2 there, I don't have enough information. If I have 1,000 points clustered in a tiny spot and 1 point that's way different, now I have information. I can say, oh yeah, that 1 point looks a little different, but I only can tell that, or I can tell that primarily because the additional number of data points that back up the claim. Also, you may have cyclical behavior. So think about a number of items sold. And let's say that you run a shop, number of items sold over the course of a month. Well, certain days of the week, shops tend to have more traffic than other days. Certain times of the day, shops tend to have more traffic. If you're running a grocery store, Tuesday afternoon, 2 p.m., usually not a really busy time for grocery stores. However, Saturday afternoon, 2 p.m., very busy time for a grocery store. So if I only have Monday through Friday data and then I plot Saturday data, it's going to look anomalous because we're not used to that large amount of traffic. So it's important to understand the domain is what I'm getting at. Do you need time series data? Well, no, not necessarily. You don't actually need time series data. In fact, I mean, I showed you an example where we don't have time series data. This is over 1 week of NFL football, and time is neither of those attributes there. It was just collected in one time frame, and time frame here can be rather loose. As long as the data points are relevant enough to each other, they have the same operation function, in other words. So what do I mean by this? Well, we can assume that there is some correlation in the NFL between passing yards and points scored on offense. And as a Buffalo Bills fan, having dealt with decades of terrible quarterback play and terrible passing, I can tell you this correlation is true. And now having a quarterback who can actually pass the ball and get lots of yards and lots of points, yeah, it's true. But what's interesting about the NFL is that the game has changed significantly since, say, the prior time Buffalo had a good quarterback, which was the early 90s. The game was much less of a passing game by that point. The league has changed significantly toward being a passing driven league. And if you compare stats from the 90s to stats from today, there's a radical difference between the two. Stats from the 70s to stats from the 90s, radical difference between the two. And so if I were to plot 1 week in 1978 and 1 week in 2019, those would actually have different operation functions. It's the same sport, many of the same teams, the same overall rules, but the function that kind of takes points based on passing yards that we're assuming changes significantly. So I wouldn't expect them to follow exactly in line. And that's where we no longer have one data set. So long story, but getting to time series is not required, but you want to make sure that all of your data follows the same underlying function. And that function can change over time, which means that you don't necessarily want to just throw all of history together unless you expect that the function hasn't changed. So let's talk now about some statistical techniques that we can use to track anomalies. We've talked technical definitions. We have some feeling of what an anomaly is, but how do we calculate that? Well, there are literally dozens of techniques. There are entire books on this. I've read entire books on this. I've got another one that I'm currently reading through. There's a story behind that, but we'll talk about it some other day. But there are some commonalities between a lot of these methods. And one of them is that if points are clustered near each other, however we define near, if they're clustered near each other, this makes a thing less likely to be anomalous. If it happens a lot, it's not anomalous. Also, there tend to be relatively few outliers and therefore relatively few anomalies. So we can isolate those. We could say, I expect that the bulk of data will be non-anomalous. It will be normal data. With time series data, we also expect that changes are gradual over time. You think of a curve, like let's say you're driving a car, you're at a stop, it's at a red light, light turns green, you hit the accelerator. You don't instantly go from 0 miles an hour to 70 miles an hour to 10 to 85 to 28 to 44, and then now you're at the speed limit. No, you start at 0 and you increase as you put your foot on the accelerator. You're going up and up until you get to 44. So we expect gradual curves in a lot of natural phenomena. If I jumped from 0 to 60 to 10 to 85, I would expect my speedometer's broken. It's not that I'm breaking the laws of physics. It's that my measurement tool is not correct. So if I see drastic changes, that's an indication of an anomaly in a point to point. We can see drastic changes over time. That's not necessarily anomalous, but a huge jump in one day or a huge jump in one moment, yeah, probably an anomaly. But trends and seasonality also affect this analysis. So as an example, going back to the store, retail stores have a set of days called Cyber 5. Starts Black Friday, the day after Thanksgiving. It technically starts on Thanksgiving, and then it goes through Cyber Monday. So you have Thanksgiving, Black Friday, you've got Saturday, Sunday, and you have Cyber Monday. Those 5 days make up a large percentage of traffic for online sales, for in-store sales over the course of a year. And if you have data from August and then you see data from Black Friday, that will be anomalous. But if you have 5 years worth of data, you can see, okay, I know Black Friday is going to be large. The fact that I got a large result is actually not anomalous. All right, standard deviation. This is a calculation of variance in our data. It's the square root of variance. And the whole idea here is as variance increases, the number of possible options that we would expect increases. So if I have a job satisfaction score and I say our mean is 50, and our standard deviation is 5, then I would expect, this is the blue line for that arc, I would expect, it looks like 35 to 60 or thereabout, that seems to be the vast majority of entries. If I get an entry that's 90, that'll look weird. If I get an entry that's 10, that'll look weird. But if we increase the variance, we increase the standard deviation. And if I increase it enough to, let's say, 20, well, if I got a score of 90, it's not common, but it's not going to be weird. I'll get a fair number of scores above 90. Like any value in here from 0 to 100 is actually fair game as far as this is concerned. So standard deviation matters a lot. And that's another way of saying that the more packed in, the tighter your data elements are, the more likely that a thing that's a little further away will be the anomalous thing. So the things that are packed tightly together, probably not anomalous. And the closer they're packed together, the smaller your standard deviation. For a normal distribution, I'd mentioned 99.7%. Where this comes from is if you have a normal distribution, about 68% of values are within 1 standard deviation of the mean, 95% are within 2, 99.7% are within 3. Usually we look at 3 standard deviations from the mean and say, if you follow approximately a normal distribution, anything beyond that, you have a 3 in 1,000 chance of being out there. That's uncommon enough that in many circumstances we would assume that's an outlier, and it may be of interest to us and therefore an anomaly. But standard deviation is not the best thing in the world because it's sensitive to the very thing we want to track in outliers. So suppose I've got these 6 data points. If you get the standard deviation of those 6, then it's 0.85, and the mean is 8.65. Now, as soon as I add a single outlier, a 1.9, my standard deviation trebles. It goes from 0.85 to 2.67. And my mean drops almost a full point just by one outlier. If I have a second aberration, then we may ignore that aberration. So if I have another item like a 5.1, basically what I'm saying here is our 95th percentile mean plus or minus 2 standard deviations. Our original range would say 6.95 to 10.35. Our new range says 2.35 to 13.03. So the fact that I had one acknowledged outlier in my data set stretches out the range so much that new things that are probably outliers now are considered normal. And that's just one data point. It's an extreme data point, but it's just one. How do we fix that? Well, this is where we get to robust statistics and MAD, where I get mad. Median absolute deviation. This is a robust statistic, and it can handle a limited number of outliers before breaking down. But that limit is much higher than the case of a mean and standard deviation. So what is MAD? The MAD is the median of our value minus the median value. So try that one on me again. Well, let's do this again. I've got our same number set. This time I'm going to calculate the median. So how do you calculate median? Well, calculating a median is a lot like being in prison. What you do is you find the biggest, meanest, nastiest guy and you shank him. But then you have to go beat up the smallest guy. You don't want him taking over after you. And you repeat this process until you end up with either 1 or 2 data points left. And I have 2 here. So what I'm going to do is take the midpoint between these 2. And that is, in fact, 8.75. So the MAD is each one of these data elements minus 8.75. And it's probably best not to ask how many times I've tried this in prison. Results may surprise you. So we find 7.3 minus 8.75. And by the way, take the absolute value of that. So 1.45. 8.2 minus 8.75, 0.55. And on and on and on. You take the median of that. And this is 0.55. So if we say median is 875, MAD is 0.55, let's add an outlier. And here we've got our 1.9. What this has done is we strike it first. And we also strike the biggest guy first. So we're actually striking the outliers first. Now it does move our new median to 8.4 instead of 875. And it does move our MAD to 0.9 instead of 0.55. But you notice, it's not a big difference. And in fact, if I bring in 5.1, I could use 3 times the median absolute deviation and still catch 5.1 as an outlier. So Samir has a question. Could you please clarify the following? Do we need to define an anomaly before we can use a machine to detect it? Or can we somehow specify what is normal and then a machine would hopefully detect some potential anomalies that we weren't aware of? That is a really good question. So anomaly detection can be supervised or unsupervised learning. Supervised learning means I know the answers. I have labels that tell me what the correct answer was. Yes, this data point was an anomaly. No, this data point was not an anomaly. So there are supervised techniques for anomaly detection. In practice, that is really uncommon because in most cases, we don't necessarily know up front what the anomalies were, and we don't have that labeled data. Instead, we use unsupervised techniques more generally. So unsupervised, I don't know what I'm looking at, but I have a feeling that if I follow this process, something will shake out from it. This MAD, this is an example of an unsupervised process. So I'm telling you 5.1 is an outlier, but we don't have some label that says 5.1 was an outlier or that 5.1 is bad data. It may actually be that 5.1 is not bad data, but it still is marked as an outlier and something for us to review and understand. So we don't necessarily tell the algorithm what is normal. Instead, we use those rules of thumb that things clustered together are usually normal. Things that are spatially close to one another or that are relatively close in terms of their various dimensions, they are going to be less likely to be anomalous. And that there are relatively few anomalies. We may give a percentage. There are only so many percentage of anomalies. And so if you see more than that number, then some of those probably are not anomalous. Just show me the ones that are furthest off from expectations. So yeah, great question. And the answer is generally we don't even try to label data. It makes it harder to analyze. It makes it harder to see if we're right. And for that, this is where you kind of hand label data after the fact, but we don't use that for training typically. If you do happen to have really good labeled data, anomaly detection becomes a lot easier because now you can basically create a classifier. I mean, at that point, it's a classification problem. And it's, yes, this is an anomaly. No, this is not an anomaly. And there are plenty of classifiers available for that purpose. Okay, we have a trend with an anomalous jump. I mean, I think we can all agree this is a trend. This is an anomalous jump. How do we separate the jump from the trend? And the answer is pretty simple. It has nothing to do with prison. It has to do with kind of rotating your head a little bit. See, what we do is we detrend. In other words, you fit the data with a line. And I'm fitting it with the pre-anomaly line, so we can see that yellow line really well. And then you kind of tilt your head a bit until that line is straight. It's horizontal. Now I measure the distance from the top of the line, from the line to the element. And that way I can see, is this distance more than what my other points look like? Obviously here, these points are very close to the line. And then we start getting increases, and this one comes back and a little high, but it's closer. So that's difference analysis. That's detrending. There's another concept, change point. And this goes back to the accelerator on a car. If I have a major change, if I have an abrupt shift in my time series data, then I'm likely to have an anomaly. And these three bars are indicators of periods where it seems like we had an anomalous change. We went from a fairly smooth curve to a massive jump and then a massive drop. And that's indicating this is interesting. This is not usually how things go over time, and therefore worth investigating further. Now, we can also do every one of these techniques when comparing the differences in points if you have an ordered sequential data set. Usually that sequence will be over time. So if I have all of these data points, they represent points in time, maybe individual months or individual days. I can get the difference between them, and that's the yellow bar, yellow set here, and I can do all of the same analysis. Looking at MAD, looking at mean versus and standard deviation, change point analysis, detrending, and reviewing that. So all of the techniques work normally and also with deltas from the prior data point. But really that only works if you have sequential data. We've pulled this data at different points in time, or if there's another natural sequencing that makes sense. Done a lot of theory. Now let's implement some practice. So we're going to build an anomaly detector in .NET. Before we do that, there are quite a few packages that give you a lot in R, in Python, in .NET, and as web services. So I don't recommend building your own necessarily. Everyone get ready for the F# code. You know me too well, Kevin. You know me too well. So I don't necessarily recommend that you start from scratch. There are several really good projects that have implemented academic papers that have been digging into this stuff for decades. And I would start with one of those. And in fact, we are going to start with ML.NET. But if for some reason the packages don't do what you want to do, or if you want to roll your own for just to learn more about anomaly detection, you can. I would check out in .NET a project called MathNet. And this is a series of .NET libraries for numerical and statistical analysis. So within this, you could actually implement all of the things that I talked about in the prior section. So you could implement MAD, interquartile ranges from MAD. You could implement mean and standard deviation, number of standard deviations from the mean. You could do change point detection. You could do difference-based analysis. And fairly quickly, I mean, most of that stuff is 1 line, 2 lines, 3 lines of code, whether it's C# or F#. So that can be worth playing around with over the course of a weekend if you want to. But at the end of the day, I would still recommend stick with a package that has implemented things, because you could get much more valuable techniques than just the basics. Many of these sorts of tests, as I mentioned, those are one-liners. Now, another alternative, I could use ML.NET. In fact, we'll use ML.NET. This is a library for machine learning in the .NET space, actively maintained by Microsoft, supports both primary languages for Microsoft's .NET platform. Sorry about that, VB folks. There are a few preparatory steps. I'm assuming that you're running this in Visual Studio Code because you don't want to pay for Visual Studio. You could also do this in Visual Studio, obviously. But if you're at the command line, .NET new, and I have to specify the language as F# because Kevin asked me to. And I'll give it a name, Basic Anomaly Detection. So I jump into that folder and I say .NET add package Microsoft.ml and Microsoft.ml.timeseries dataset. Those are 2 NuGet packages available for ML.NET. And xplot.plotly lets me draw really cool graphs. It's an F# specific thing. So let's jump into my demo code. And I'm going to have to see which one of these many fine. There we go. That is my Visual Studio code. So you can see I'm in basic anomaly detection already. I'm going to hide that one. And what are we going to do? We are going to look at the most anomalous of data sets. This is the GameStop stock data set. So if you're not familiar with it, GameStop is a company that sells games and other stuff like games. And for a pretty long time, their stock price was kind of low. I mean, for months, it was pushing $4, $3. And there's a whole story around this. I don't have time to get into the full story. It's actually a really interesting story. And there were a few people who, at this point in time, in about September, were saying GameStop is actually a legitimately they are a stable company. They have a lot of cash in the coffers. They're drawing in enough money. They're not losing any money. They're pretty stable, even in the year 2020. And so they were basically giving signals, hey, buy this stock. And the stock stayed stable, continued to stay stable until the dam burst in mid-January of 2021. And it went from low teens to $38 to $350 by January 27th. And then it lost $100, then it gained $100, and then it went to 140, and then it dropped into the 40s and 50s, and then it jumped up again. It hit like 269, 275, and it bounced around considerably since then. And now it's basically stabilized, for some sense of the term, anywhere from about $140 to $200 in terms of share price. So if you did buy back in September, you're doing pretty well for yourself. But most people did not buy back in September. Instead, a fair number of people bought like right about this day at $300 and some dollars. And most of those people either lost out because they sold too fast, or they cashed out right when the stock hit 300 again and said, oh, I'm out now. But that's neither here nor there. Let's build a program that analyzes that data set and looks for anomalies, because there's probably one or two of them. So we are going to look at Microsoft ML data, and we've got some classes here, like price data. So price data actually is going to be the shape of this GME data set. And data set has a date. It's got an open price, the high price, the low price, the close price, and then adjusted closing price and volume. I'm going to be focused on the closing price. That's the only thing I'm really going to focus on today. But I still need to build out the shape of the file so that I can load that data pretty easily. I have price predictions. Given a date, what do I expect the price to be? And that's what so this is how our process is going to work. We're essentially generating a prediction of what we would expect the price to be, and determining if the difference from that prediction is significant enough to mark it as an anomaly. This is one technique for anomaly detection. This is one where you're essentially, it's a model-based technique. There are other techniques like the statistical techniques that I talked about, and also clustering similarity-based techniques that you can use. So this is just a third way that you could do it. And we'll load gme.csv into a data view, which is an ml.net construct. We load that data from the text file. This is intended to be sort of like the Python or R code loading. So loading a data frame in R or in Python is really easy compared to .NET. This is intended to make .NET a little easier to do. So I have my file, I have my shape of what I expect the data to look like, and I have a class that gets generated as a result. I have a few parameters to determine how far back we're going to look to determine if something is an anomaly. And how confident are we, or do we need to be before we discern that this is anomalous? And then we have this anomaly pipeline. So I'm doing anomaly detection and also change point detection in the same script. So you'll see two sets that are very close to each other. We have a prediction, the closing price, and we're going to say, show me if it's anomalous. And by the way, if it's a high anomaly or a low anomaly, I want to know both. You could do this as one-sided and say, I don't necessarily care if it's higher. I want to know if it's an anomaly that's too low. Maybe I have a problem with my model, for example. Whereas if it's high, sweet, I made extra money. And with change point detection, there are a couple of different techniques for how we determine the change, whether or not this is a sharp change or a smooth change. Okay, so we fit our data to a model. The fit method is based a lot like scikit-learn's fit method. We transform this data frame into something that we can use in our model. So I have this trained anomaly model that's expecting certain inputs. It's expecting an input called close, and it's going to give us an output called prediction. So we're reshaping this data to fit what we need. We're going to generate anomalies of the type price prediction based off of that transformed anomaly data, and do the same for change point. And then down here, the rest of this code. So the majority of this code is really just to draw a scatter plot. I won't get into that because it's not an anomaly detection, it's visualization. So let's .NET run this puppy, and we're going to see how well it works. Takes a moment to kick off, but once it kicks off, it's going to scan through very quickly, and hopefully we get back a chart that looks a little like this. So here are our GameStop price anomalies. We have basically no anomalies until, what is that, August of 2020, when things start moving. And then we have anomalies galore for this stretch of time in early January into sometime in February. So like late December, getting into January, and then things go crazy. What's real interesting is that for a stretch of time from about February into May, there are technically no anomalies. The reason why is that over the course of a couple of days, you range from $40-some to $350. And so, yeah, any point within here is fair game. And then eventually it stabilizes, and we can see that anomalies start picking back up again. There's another up cycle, and then there's a down cycle, and then there's a jump. So we can see that, you know, over the course of this time frame, we're picking up a lot of anomalies. Now the question is this all of them? That's a fair question. And that's where we get back to the fact that this is unlabeled data. I can't tell you somebody's come down from on high and declared that these days are officially anomalous. All we can do is look at them, investigate them, maybe ask a question of why wasn't that considered anomalous? And try to understand the model underneath versus having something tell us, here's our set, and compare it to what that thing has told us. So we don't have an external authority that officially determines that this thing is an anomaly. It's up to us as humans to interpret, understand, and decide if we missed something. So that was anomaly detection in ML.NET in, what would I call that, 40 lines of code? I mean, if I come up here, technically we're at 97 lines, but look at this. The first 45 or so were just load the file. So, and this also included chain point detection. So it's like 40 lines of code that give you anomaly detection in your .NET code. Even in C# it'd be about 40 lines of code. The majority of it really is just define your classes. All right, last thing we're going to do, we've got about, 10 minutes left. We're going to try to use Azure Cognitive Services. We can use external APIs. AWS has SageMaker. Amazon has Cognitive Services. Google has something. I don't know. I don't really pay attention to GCP. That's a blind spot for me. But if you do know, put it in chat. I'd actually be interested. I just apparently not interested enough to do a Google search for Google machine learning. Nonetheless, Azure Cognitive Services does have an API for anomaly detection. It's a REST API where you can feed it data and it can take back different values. So it can give you back whether or not this thing is anomalous. You have to create a resource in Azure, save your key and endpoint, and I save them in an environment variable to make it easier, and create an application, work with the API. So when it comes to creating the anomaly detector, you go to the Cognitive Services Marketplace and you say, I want me an anomaly detector. You click that and you fill out some details. Choose your subscription and resource group. Where do you want it to be? Give it a name. And by the way, there's a free pricing tier. So you can do 10 calls per second up to 20,000 per month. If you want to play around with this on your own time, that's a great option. Then, once it's created, you go in resource management, select keys and endpoint, and we have the keys. So I can copy the keys. I can copy my endpoint. And I'm going to save those as environment variables, which if you're not familiar with this in CMD, I can use setX to set an environment variable. And I give it a name, and I give it a blurred out value. So setX, environment variable name, environment variable value. Then you can use the Anomaly Detector API. And if you have an Azure Cognitive Services Anomaly Detector endpoint already set up, you can go to algoevaluation.azurewebsites.net. This is Microsoft's demo site for anomaly detection. So they show you ways that you can implement anomaly detection using their Cognitive Services API. And we can see the anomalies as they're laid out here. It's a pretty cool website. But it requires that I put in my subscription ID, and I don't want to share that over broadcast. So we're going to skip past that and go to my demo instead. My demo here, we're going to look at a subset of this data. I don't want to try to burst sending too much data to Cognitive Services at once. But here's my program. This program, ironically enough, would be a lot easier to write in Python or R than in .NET, because Python especially has an SDK specifically for Cognitive Services to hit those APIs very easily. For .NET, we have to load Cognitive Services.anomaly detector NuGet package and import the anomaly detector and anomaly detector.models namespaces. I then have to load my data. Unlike ML.NET, Azure Cognitive Services does not have a data frame concept, so no relatively easy way to load a CSV. F# has a relatively easy way to load a CSV. It's called a type provider. So this is a CSV provider. It's built into the f#.data library, loaded from NuGet, and lets me read a file like gme.csv and generate a type or a class off of that file. So I have stocks. And then if I come down here to my main application, by the way, I have already set anomaly detector key and endpoint on this machine. So I'm going to get those environment variables. I'm going to create a client given that endpoint and key. And then I'm going to generate a request on that client, passing in the contents of gme.csv. So let's see what create client does. create client takes endpoint and key and says, create a new anomaly detector client. Send in my credentials, and here's my endpoint location. And then returns that resulting client. Then I have the client, and I need to generate a request. So what does a request look like? Well, I have a file. I'm going to load that file and fill it up in this type of stocks. So I'll take all the rows from this file and then fill it up and call this lines. Then in lines, I'm going to reshape. For each line, I will create a new point. Now, this is a Cognitive Services Anomaly Detector.models.point object. And that point object needs to have a date, and it needs to have a float for a value. So this is specific to this Cognitive Services API call, means they need time series data. They won't take non-series data. Well, fortunately, I have time series data, so we're okay here. I'll take that data, turn it into a list, and then actually turn it into a resharp array. So, a resize array. This is, if you're familiar with C#, this is a list class in C#. This is an IEnumerable in C#. So I have to actually make it a list because Cognitive Services NuGet package requires a C# list. And then generate a request based off of this. So I've got my C# list and my granularity that tells how frequently this data gets changed. So this is daily granularity. Now I'm going to perform detection on the entire sample. And what I'll do is I have a client, I have a request, I will send the request to the client. So client, give me back an analysis on the entire data set. And here's my data set. I will hang up and listen to your answer. And so it waits for the task to finish up. And basically, it's going to detect my anomalies. I'm going to take the response that comes back from calling detect anomalies and then check each record. First, I'm going to see, do I have an anomaly? So this actually returns back a list of Booleans. And for all of the anomalies, I'm going to combine them. So the term is zip in a functional programming language, but don't think of WinZip. Don't think compression. Think of like a zipper connecting together. So I zip those together and I filter specifically where this is an anomaly. And I determine, were there anomalies? 0 anomalies, 1 anomaly, multiple anomalies. Then, of course, I want to know, what were the anomalous dates? So let's see if this works today. We're going to .NET build. We're going to, all right, my fingers weren't crossed, but it still succeeded. That probably means the next thing will fail. .NET run. Oh, hey, it worked. And it detected 1 anomaly. On March 24th, the closing value was $120. So let's see. This, like I said, this is a different subset. And you may say, well, 277 seems like a pretty high value. So why 324 when the closing value was $120? And if you look at the open date, the open value, that's a little easier to see. So the open value on 325 was close enough. But basically, this was a drop of 30 some dollars. And then the next day was an increase back into the 190s region. So we had 200s and we had a drop, then we had a big drop and then a big increase that brought us back up here. And it stayed in that 190 range for the rest of the data set. So it actually makes sense why this would come back as anomalous. So cool, that worked. By the way, if you want to create the package, we have this console, add Cognitive Services Anomaly Detector and F#.data, which I already talked through both of those. So we're ahead of the game, which is good because we're right at time, which means I need to wrap up. Over the course of this talk, what have we done? Well, we've talked about the concept of anomalies, talked about Gestalt psychology, talked about Buffalo's quarterback stretch of bad luck, I think we probably also did some looking at code and some .NET packages making life easy for us. If you want to learn more, you can grab the code, you can grab the slides, you can get links to additional resources. All of that is available. csmore.info/on/anomalies. If you have any questions at all afterwards, please do feel free to reach out to me. I will give you my email address that you can hit me up at, or my Twitter handle that every once in a while I show up on Twitter. And feedback, feedback, feedback. It's not just what happens when I stick the microphone too close to the speaker. It is important to all of us. And so please do rate, review the session. Let everyone know what you thought. With that, I want to say thank you so much, everybody. Have a wonderful rest of your conference.
Thanks, Kevin. That was awesome. If you do have any follow-up questions, especially if they're really short, I'm sure Kevin don't mind sticking around for a minute or two, and please put them in your chat now. Ask away and you get what you asked for.
Oh, wow. A short elaboration on differences between model-based statistical and clustering methods for detecting anomalies.
Obviously, Samir has never talked to you because there is no short.
I'm reasonably tall in real life. Yes, you're right. Okay. Statistical differences, statistical analysis. I'm looking at the distribution of data and looking for things that don't fit that distribution. So that was where we talked about MAD, where we talked about mean and standard deviation. So I'm plotting the data and I'm seeing what is way off. A model says, I have some understanding of the world and I want to see how far off this data point is from that understanding of the world. So if I look at passing yards versus points scored, I expect that there is a linear model or something approximately linear where more passing yards, more points scored. If I have some data points that are way off from that, then that is anomalous. Last, clustering methods. I don't necessarily have a model of how I expect things to work, except that data points that are close together are less likely to be anomalous than data points that are far apart. So if I have a bunch of data points that are all clustered together, then those are less likely to be anomalous. So the question becomes, how far apart are these data points? And how far apart are normal data points within this set? So that is a really short comparison of the three techniques. And based on the information that you have. Models, you're going to need more info. Statistics, you're going to want to understand the distribution. You can fake it with normal, but not everything's normally distributed. And clustering, typically that's going to be more valuable with multivariate data, but clustering is probably the go-to technique once you get to more complicated problems and you don't have a model.